Have you ever wondered whether there are any microplastics in your drinking water? How well can scientists measure microplastics anyway? Hello, friends of facts, and welcome to Fantastic Studies and Where to Find Them. Join us for some exciting research from scientific papers. In 2021, Weber and co-authors published a study on the investigation of microplastics in drinking water in the German city of Rüsselsheim. Never heard of it? Anyway, it's close to Frankfurt and has 66,000 inhabitants. Never heard of Frankfurt either? Well, that's somewhere in Germany. What exactly do scientists mean when they say microplastics? The term refers to solid plastic particles consisting of polymers and additives. Micro means they are small, at least smaller than 5 millimeters. Most microplastics are smaller than 10 micrometers. This is about 1/10 of a hair, and even smaller than the dust particles on your floor. Microplastics are found nearly everywhere in the environment. They have been detected in seawater, fresh water, and sediments. Not surprisingly, they have also entered the food chain. They have, for example, been found in shellfish, fish, and bottled drinking water. Consequently, microplastics have been detected in humans as well. It is still largely unknown whether microplastics can cause harmful effects in humans. Possible effects include oxidative stress, inflammation, as well as toxicity to the immune system and the brain. The authors analyzed water samples from house connection and water transfer stations. In this study, they only analyzed microplastics larger than 10 micrometers. In most locations, they did not find any microplastics in drinking water. There was one exception though. Samples taken from an educational institution contained copper phthalocyanine particles. Not many, mind you. On average, there was just one particle in 10 liters of water. Still, where does it come from? Copper phthalocyanine is a common blue pigment used to dye plastics. Most likely it originated from drinking water pipes used in that building. You can probably imagine that finding a single tiny particle the size of a fraction of a hair in 10 liters of water is not an easy task. So how do scientists do it? And how certain are they that they did not overlook one of those minuscule bits? Here's what the authors of this paper did. They attached the device to the water tap, which contained a filter that let water and smaller particles through, but retained everything larger than 10 micrometers. Then they analyzed the filter using Raman microspectroscopy. This has nothing to do with delicious Asian noodles, but rather with special microscopy for very tiny bits and pieces. But there are many additional steps to take into account. First, scientists need to carefully avoid contamination. Today, plastic is everywhere, also in laboratories. Therefore, they work in sterile and clean environments and avoid plastic containers and tools wherever possible. Still, they cannot avoid contamination 100%. To account for that, they take along so-called blank samples, which help determine the microplastic background signal. The background signal is then subtracted from the water sample value to correct for potential contamination and estimate the real signal. In this study, background signals were low, but they can cause problems. For example, your water contains 10 particles, and your average background contamination is 5 particles. Do you find something here, or is it just background noise? Then again, if you find 100 particles in your sample, you will be more confident to conclude that you detected microplastics in your water. That means the higher and the more variable the background signal is, the harder it is to identify low levels of microplastic pollution. Second, in addition to microplastics, even clean-looking drinking water may contain other tiny particles, for example, inorganic ones like metals. They could come from pipes or remain in the water despite treatment. In order to remove them, the authors in this paper used a strong acid to dissolve them. While that worked well, the authors needed to make sure that microplastic particles were not affected by this treatment. Some were not, some were just a little. In the end, it's a trade-off. Do you want your plastic particles perfectly unaltered, or do you want to avoid accidentally counting non-plastic particles? Third, the measurement method in itself has an impact on your results. Some methods simply rely on counting particles using a microscope and a computer software. They are good at determining the number, size, and shape of particles, but cannot tell you what those particles are made of. Are they really plastic particles? If so, which kind of plastic? Others are excellent at answering those questions, like Raman microspectroscopy. Unfortunately, they don't tell you which size and shape a particle is. This is one of many reasons why scientists need to be careful when comparing results from different studies. Fourth, scientists are a lazy or, let's say, efficient lot. They don't count every tiny particle on the entire filter area. Instead, they put an imaginary checker pattern onto the filter area. In this study, the scientists took more than half the filter area into account, for example, by only analyzing the white squares of the pattern. This is called subsampling. From their subsample data, the authors extrapolated to the entire sample. If you count 50% of your filter area, you multiply your results by 2. However, this can lead to extrapolation errors and result in the over- or underestimation of microplastics in water. Fifth, you need to take your losses into account. What if you accidentally wash or brush away some particles? That is where recovery comes in. Recovery samples are additional samples intentionally contaminated with a known number of microplastics. You treat them like all your other samples and measure the number of microplastics with your method of choice. Then you compare the number of measured to the number of added particles. If you only measure half the particles you know you added, you multiply the results of your real sample by 2. For example, you know you added 100 particles to a sample, but when you measured it, you only detected 50 particles. That is only half of what you added, and your recovery is therefore 50%. When you detect 30 particles in a real sample, you assume you probably also lost half of them on the way. Therefore, you assume there must have really been 60 particles. Since there is no standardized reference microplastic set you can buy at your local laboratory supplier, you need a workaround. For example, nicely rounded plastic balls of various sizes. Of course, real microplastic are not perfectly rounded spheres. In fact, they are quite unlikely spherical, since they are subject to abrasion and degradation. But let's come back to our paper. In this study, like in our example, only half the added particles were recovered. Thus, the authors corrected their measurements by a factor of about 2. Sixth, statistics are a fickle thing, easily misinterpreted. For example, there are 8 times more microplastics in one sample than another, and the difference is statistically significant. Sounds important, right? But what if there is only 1 particle in the one and 8 particles in the other sample? Significant it is, but overall it's not really relevant. Keep in mind that in the environment, wastewater and drinking water, the number of microplastic particles ranges from 0 to 1 billion per cubic meters. Therefore, a difference of 1 and 8 particles is just not that meaningful. Overall, does that mean we are clueless? In our personal opinion, not at all. It just means that research on microplastic pollution is ongoing, and there are still many open questions and uncertainties. Therefore, when interpreting microplastics data, we should keep those uncertainties in mind. Interpretation and comparison of research results would, however, be a lot easier with standard methods and procedures everybody agreed on. To come back to the questions we asked in the beginning, have you ever wondered whether there are any microplastics in your drinking water? If you live in Russelsheim, your drinking water is not contaminated with microplastics larger than 10 micrometers. But particles from plastic pipes can enter drinking water at low concentrations. More research in more cities all over the world is required to provide a general answer to that question, though. Ideally, such research would also include even smaller plastic particles. And how reliable are scientific measurements of microplastics? While microplastic measurements are reliable, their interpretation and discussion needs to consider current scientific limitations. Most importantly, keep in mind that different methods may not provide comparable results, and especially low numbers of microplastics are difficult to quantify correctly. Would you like some inspiration to reduce plastics in your everyday life? Have a look at those YouTube channels here. Thanks for watching and see you soon.